Nucleophilic substitution reactions. When a strong nucleophile replaces a weak nucleophile, this reaction is called a nucleophilic substitution reaction. But what is a nucleophile? A nucleophile is an electron-rich species which donates electron pairs to electron-deficit species. These are a few examples of nucleophiles arranged in decreasing order of nucleophilicity. Let's see this reaction. Here, Nu and X of Rx are both nucleophiles. The nucleophile reacts with Rx, giving Rnu and X. This Nu is any nucleophile stronger than X, and so, this substitutes X, forming Rnu and X-. This reaction proceeds by two ways. First, by molecular nucleophilic substitution, or SN2. Here, molecules of the reactants are involved in one-step reaction. That is, here both Nu and Rx are involved in the one-step reaction. Thus, the rate of the reaction depends upon the concentration of both the reactants. Second, unimolecular nucleophilic substitution, or SN1. Here, reaction takes place in two steps, and the rate of the reaction depends upon the concentration of the first reactant, that is, Rx. Now let us understand SN2 reactions in detail with mechanism. SN2 reactions are bimolecular reaction with one-step mechanism. That is, reaction proceeds in one step. Example: CH3Cl plus KOH gives CH3OH plus Cl-. OH of KOH is a stronger nucleophile and attacks CH3Cl from backside. At the same time, leaving group Cl leaves. The formation of CO bond between C and OH and breaking of CCl bond both take place simultaneously, and thus a pentavalent transition state is formed, which is very unstable. As Cl leaves, alcohol, that is, CH3OH is formed. Alcohol thus formed has inversion of configuration. The OH gets attached to the opposite side of Cl. Whenever a sigma bond is formed, a sigma star bond is also formed due to antibonding. So, OH forms sigma star bond and shows inversion in its configuration. To summarize SN2 reaction: more stable the transition state by electron leaving group, more will be SN2 reaction. More the steric hindrance, less will be SN2 reaction. This reaction requires the approach of nucleophile to the carbon having leaving group. The presence of bulky substituents on or near the carbon atom will reduce the rate of reaction. Primary alkyl halide will show more SN2 reaction than secondary or tertiary alkyl halide. Better the leaving group, the faster will be the rate of reaction. So, reaction will be faster with Ri, then Rbr, then Rcl, then Rf. When the concentration of nucleophile is higher, the size of the nucleophile is smaller, and its ability to give electron, that is, nucleophilicity, is better. Then SN2 is faster. SN2 reaction takes place in presence of polar aprotic solvent. That is, solvent which is polar and lacks an acid proton. Example: acetone, DMF, THF, DMSO. The key point is that it is a one-step mechanism. By molecular reaction, backside attacks of nucleophile takes place to the carbon with leaving group. Pentavalent, unstable, transition state is formed. The formation of CO bond between C and O and breaking of Cl bond takes place simultaneously. The product, alcohol, which is formed, has inversion configuration. OH gets attached to the position opposite to that of Cl. SN1 reaction. SN1 reaction is a unimolecular reaction which takes place in 2 steps. Example: a tertiary alkyl halide, CH3-CBr, reacts with KOH and gives a tertiary alcohol, and Br- is obtained. First step involves only one reactant, that is, CH3-CBr. It involves the reactants with leaving group Br attached to the carbon. Here, Br, the leaving group, leaves, and carbon cation, which is an intermediate product, is formed. The formation of carbon cation is a slow and reversible reaction, and hence, it is the rate-determining step. O of OH forms bonds with carbon with positive charge, forming alcohol. Here, in this example, tertiary alcohol is formed. 2 possible products can be formed. 1. Where stereochemistry is retained. OH forms bond with carbon in the same side as Br. 2. Where stereochemistry is inverted. OH forms bond with carbon in the opposite side of Br. Key points are: more stable carbon cation, more will be SN1 reaction. More ease of dissociation, more will be SN1 reaction. As tertiary alkyl halide dissociates faster than secondary, which is faster than primary, tertiary alkyl halide shows more of SN1 reaction. Better the leaving group, faster will be the rate of reaction. SN1 reaction is not affected by concentration, size, or nucleophilicity of nucleophile, as nucleophile is not involved in rate-determining step. Polar protic solvent favors dissociation of bond, along with the stabilization of ions. Hence, it favors SN1 reaction. Polar protic solvents are solvents which have at least one hydrogen atom connected directly to the electronegative atom. For example, water, alcohol, acetic acid, etc. SN1 reaction is unimolecular reaction with 2-step mechanism. So, first step is formation of carbon cation, which is a very slow and reversible reaction. Since it is slow and reversible, it is the rate-determining step. Second step is carbon cation reacts with nucleophile, forming alcohol. OH can be attached in the same side of Br, or it can be attached in the opposite side of Br. If attached in the same side, the stereochemistry is retained. If it's in the opposite side, we see inversion. Rate of the reaction depends upon the concentration of one reactant, alkyl halide, that is, the carbon atom with leaving group. This is how SN1 and SN2 nucleophilic substitution reactions take place.